Hello, my name is Vladimir Korikov, and this is the Domain-Driven Design in Practice course, extending the bounded context with aggregates. In this module, we will extend our snack machine model with the actual purchase functionality. Along the way, we will discuss best practices for working with aggregates and we'll see how they are applicable to our project. Currently, our snack machine model doesn't actually make any purchases. It just appropriates whatever money a user inserted without giving anything back. Obviously, that's not how real snack machines work, and we need to extend the model's functionality. So what are the requirements for the functionality we need to implement? First of all, the snack machine should have 3 slots, each of which may contain several snacks of the same type and of the same price. The snack machine should allow us to buy any item from those slots. There are several business rules that should be followed here. First of all, if a user inserts more money than needed, the machine must return back the change. If the money inserted is not enough or there is no products left in the slot, the user should get an error message. And finally, it might happen that there is not enough change in the machine. We should handle such situations as well. As usual, we will start with the simplest implementation possible and iteratively move towards better design. We will see how to handle one-to-many relationships between domain classes, how to combine several entities into aggregates, and how to find proper boundaries for them. Let's see how we can implement the new requirements in code. This is how our domain model looks like currently. To handle the new purchase functionality, we need to add 2 new entities, snack and slot. The snack class will contain only a name field. The slot entity should have links to both a snack and a snack machine, and also contain the information about the slot, its position in the machine, and the price and the number of the snacks residing in the slot. Alright, let's add a new class, snack. This would be an entity, so I'm inheriting it from the entity base class, and it will contain only a single name property. Adding a parameterless constructor to make it work within Hibernate, and another one accepting a name. And I need to make the property virtual. Perfect. Another entity we need to introduce is slot. Here are its properties. And I have to add 2 constructors here as well. A default one and the one which accepts all properties required to initialize a slot. This is the snack machine class. We'll start by modifying the existing test that covers the buy_snack method. Let's rename it to buy_snack trades inserted money for a snack. First of all, before we buy anything, we need to put snacks into it somehow, so we'll need to implement a corresponding method. And we will need to validate that the number of snacks decreased after the purchase. I'm placing some raw text here, which obviously wouldn't compile. You can view it as a part of the red-green refactor process. I don't have an API for this kind of validation just yet, so I cannot use the actual code here. But I can put some placeholder to not forget to do this in the future. This text acts as such a placeholder. Alright, creating the load_snacks method, the slot number where we need to put the snacks, a snack instance, quantity and price. In order to implement this method, we need to introduce a storage for the snacks, so I'm adding a corresponding property which would hold the slots the machine has. Good. It is of type iList and not just list, because Hibernate requires collections that are part of the mapping to be either of iCollection or iList types. We will talk about the collection mapping later in this course. Now we can find a slot by its position and assign a new snack, quantity and price to it. And we need to make setters for these 3 properties public here. Alright, we can load some snacks to the first slot of the machine with quantity 10 and price $1. We'll need only a single dollar to buy this snack, so I'm removing the second insert money method call. Note that we currently call the buy_snack method without any parameters. We need to somehow specify what snack we are buying. The best way to do this is to pass the position of the slot, because that's exactly how the end user would approach the task. He or she just needs to indicate in what slot the snack they are interested in is located. We've loaded the snack into the first slot, so I'm passing 1 here as well. Now we can verify that the number of the snacks has changed. It should be 9 after the purchase. Alright, let's make our code compile by adding a position parameter to this method. You can see the test fails on this line. That's because we didn't initialize our collection of slots. To do this, I need to define a constructor and assign a new list to the property. Every snack machine in our domain model will have exactly 3 slots, so we can initialize all of them manually here. Passing this as a snack machine instance to the slot, the position is 1, no snacks, and 0 for both the quantity and the price. The other 2 slots are the same, except that they are located at different positions. And just to be consistent with the way we initialize the snack machine instances, I'll move these 2 lines to the constructor as well. You can see the test still fails, but this time for a good reason. The quantity of the snacks in the slot didn't decrease as we expected. To fix this, we need to go to the bySnack method and reduce the snack number by 1. The test is passing now, very good. As you can tell, the by method still lacks some functionality. For example, we didn't return change and we don't have any validations in place. We will address these issues soon. For now, let's take a minute and discuss the design we've come up with. At this point, we approached an important topic, the notion of aggregate. In our domain model there are 2 of them, snack machine and snack. Let's elaborate on that. Aggregate is a design pattern that helps us simplify the domain model by gathering multiple entities under a single abstraction. This concept includes several implications. First of all, an aggregate is a conceptual whole, meaning that it represents a cohesive notion of the domain model. Every aggregate has a set of invariants which it maintains during its lifetime. It means that in any given time an aggregate should reside in a valid state. For example, let's say snacks have an additional attribute, weight, and we have an invariant stating that our snack machine cannot hold more than 10 pounds of snacks. This kind of validation should be performed in the aggregate so that it's not possible for the client code to add more snacks if the overall weight exceeds the limit. Every aggregate should have a root. That is the entity which is the main for the aggregate, so to speak. An important rule regarding this notion is that classes outside of the aggregate can only reference the root of that aggregate. They cannot hold a permanent reference to other entities of the aggregate. In our case, the root of the snack machine aggregate is the snack machine class. It means that entities outside this aggregate cannot keep a link to the slot entity. They can hold it temporarily though, for example in a local variable during some method, but they should get access to it via the root entity only. So in our case, if a client code is about to get information about some slot from the database, it should get the corresponding snack machine instance first, and only after that retrieve the required slot using the root entity. However, try to avoid exposing the internal entities at all, if possible. You will see this practice in a minute. We will hide the slot entity from the outside world completely. This point strongly correlates with the previous one. Restricting access to the entities that are internal to an aggregate helps protect the aggregate's invariants. Ideally, there should be no way for the client code to break the aggregate's invariants and thus corrupt its internal state. Aggregates also act as a single operational unit for the code in your application layer. Application services should retrieve them from the database, perform actions and store them back as a single object. In other words, they should consider an aggregate a conceptual whole and refrain from working with separate entities in it. Another function aggregates hold is maintaining consistency boundaries. It means that in any given time, the data in the database that belong to a single aggregate should be consistent. To achieve this, we need to persist an aggregate in a transactional manner. In our case, there shouldn't be a situation where we save to the database only the snack machine itself without saving its slots with it. The database should contain all information about the aggregate, and this information must be consistent, meaning that it shouldn't break the invariants of this aggregate. At the same time, the invariants that span across several aggregates shouldn't be expected to be up to date all the time. They can be eventually consistent. Note that while an entity can belong to only a single aggregate, a value object can reside in several aggregates. For example, there might be another aggregate and an entity in it that holds a money property. That's perfectly fine. Again, it makes sense if you replace the money value object with an integer. Any entity in your domain model can hold one. The same rules are applicable to value objects. One of the biggest questions that rise when it comes to working with aggregates is how to choose boundaries for them. Why are there exactly 2 aggregates in our domain model and not, say, 1 or 3? We could, for example, make all 3 entities belong to a single aggregate, so why it is that we have such boundaries in our domain model? Just like with entities and value objects, there are no objective traits that make particular boundaries for an aggregate. They fully depend on the domain model you are working in. The way we group entities into aggregates in different domain models can vary a lot, even if those models have the same set of entities. However, there are some guidelines you can follow in order to identify the boundaries. The main attribute that makes an aggregate is cohesion of the entities in it. Entities inside the same aggregate should be highly cohesive, whereas entities in different aggregates should maintain loose coupling among each other. It's a good practice to ask yourself the following question: does an entity make sense without some other entity? If it does, then it should probably be the root of its own aggregate. Otherwise, it should be a part of some already existing aggregate. In our case, the slot entity cannot exist without a snack machine, so it has to be a part of its aggregate. These 2 entities, snack machine and slot, comprise a cohesive group of classes, an aggregate. At the same time, the snack class can probably live by its own, so it should be the root of an aggregate which consists of a single entity. As you go along with the development process, you will receive more information about the domain. If you think the boundaries you selected initially don't play well with the problem you are solving, don't hesitate to change them. Domain modeling is an iterative process, so don't expect to find proper boundaries for all your aggregates right away. If you want to learn more about cohesion and coupling, as well as the differences between these 2 notions, you can read my blog post here. Be aware of creating aggregates that are too large. It might be tempting to include into aggregates more entities. For example, one could decide to include the snack class into the snack machine aggregate. While it might seem a good idea because it leaves us with less number of aggregates and thus with a simpler domain model, in most cases it doesn't work out well. The reason here is that the bigger your aggregates are, the harder it is to maintain their consistency and handle conflicts when several transactions try to update parts of a single aggregate at once. Finding proper boundaries is a tricky question, and basically is a trade-off between the simplicity of the model and its performance characteristics. Just to give you some heuristic, in the projects I was a member of, most of the aggregates contained 1 or 2 entities, and I don't remember an aggregate with more than 3 entities in it. It's totally fine to have a lot of single entity aggregates, so don't try to gather entities into aggregates artificially. Just follow the guideline and make sure entities in your aggregates comprise a conceptual whole, meaning that they don't make a lot of sense without each other. Note that this heuristic doesn't include value objects. You can have as many value objects in your aggregates as you want. I'd like to make an important note here about one-to-many relationships between entities. In our domain model, the relation between the snack machine and the slot classes is one-to-many in a sense that a single machine can theoretically hold as many slots as possible. Despite its name, in most cases, the one-to-many relation should be viewed as one-to-some, meaning that there shouldn't be a lot of entities on the many side. If you find a class in your domain model holding a collection of entities and that collection contains more than, say, 30 members, it's a strong sign you should revisit the model and probably remove the collection and extract the entity on the many side to its own aggregate. For example, we could hold a log of all purchases made in a snack machine as a collection in the machine itself. This design might seem compelling at first, but the problem here is that the bigger the log gets, the harder it is to maintain proper performance when working with the aggregate. In this case, it would be a good idea to extract this class in a separate aggregate and work with it apart from the snack machine. To make this separation work, we could employ domain events. We will talk about domain events in the future modules.